Good afternoon, everybody. So guests, industry partners, and distinguished researchers, it's my special privilege and pleasure to welcome you to this Research Week 24 event, spotlighting our faculty research. Just having listened to some of the conversation here over the last few minutes, I wish I could have been here all this morning, but we have an engineering accreditation exercise happening on in other buildings, which is very important as well. So to those of you who may be visiting us for the first time, I just want to welcome you to Limerick, to UL, and of course to the Bernal Institute. So we're here to address pressing environmental challenges and to discuss sustainable solutions. Obviously, all of these things in modern universities and organizations like ourselves, have policies and statements and positions on these things, but I guess the point of reflection is whether we've almost transcended that position to the point now of moral imperative. So our focus today is on sustainability, specifically in science and engineering. Our faculty members and their teams will present innovative approaches to environmental impact reduction, resource efficiency enhancement, and promoting a circular economy. So first up, we have Dr. Aleksandra Serafin, who will discuss sustainable materials in health research under the supervision of and guidance of Professor Maurice Collis. Then we have Professor Matteo Lusi and Dr. Jacky Bouanga, who will talk about their work on waste management and specifically the recovery of nitrogen and phosphorus from dairy waste streams. Following that, we have Dr. Marzena Kwapinska, who will discuss thermochemical processing of wastewater sludge and explore the potential for circular bioeconomy, and that's working with Professor J.J. Leahy. And lastly, we have Professor Ronan Courtney, who you've heard from throughout the morning, I'm sure, and Dr. Mariagrazia Proto, who will discuss ecological engineering and the bioeconomy. So I invite you to welcome these researchers and celebrate their successes and achievements over the next session. And so we embrace innovation, collaboration, and sustainability for a better future. So without any further delay, we will once again revolutionize sustainability in the next 40 minutes. So I won't delay you any further than that, and hope you have a good session. Thank you.
So basically, I lead a group here in the Bernal, a very large group, a very active group, a very dynamic group, and we do a lot of things. And this is, I can summarize it basically with two molecules. We work with hyaluronic acid, is the first molecule we work with. And what we do with that is, you might have heard of hyaluronic acid. L'Oreal, they advertise it as an anti-aging cream. What we do is we modify this molecule and we use it as a hydrogel, as a nanofiber, as you can see, as a scaffolding material, and a film for wound healing. And the idea is that there's a shortage of donors for soft tissue implants. And what we do is we want to try and recreate tissue. So what we do is we seed living cells onto these materials, and we regrow tissue, so there's no need for implantations. And Aleksandra is going to talk about that in her talk, so I'm not going to go into any more detail on that for the moment. The second molecule that we work on is lignin. And I don't know if you've heard of lignin, but it's been really fruitful for us. We've made a huge impact in this area. Lignin is a sustainable material. It comes from the paper and pulp industry. You've all heard of cellulose. Cellulose is used for making paper, and hemicellulose for maybe sustainable aviation fuels, but lignin is a waste. And there's 140 million tons of lignin accumulating around the world every year with no value. It needs valorization. So what we do is we try to valorize lignin in advanced engineering applications. Other people are working on this now as well, but they're looking at more low-hanging fruit, where they're blending lignin in with other fossil-based materials to try and get an improvement. But we're taking a totally radical approach, where we're using lignin for advanced applications. for putting real value on lignin. So we get this waste material and we convert it into carbon materials for carbon fiber, for reinforcing polymers, and they can be used in things like Formula 1 cars, aircraft, or just automotives for electric vehicles. We're also putting it into batteries for energy storage, and we're also using it for energy harvesting in wind turbine blades. We've also converted lignin into hydrogels, like what we've done for hyaluronic acid. We brought some of the learnings from that into lignin, and we use it to release drugs for human applications. And we also use it for releasing fertilizer in the same way for agriculture. And that work has been supported by DAFU. Some of the new things that we're doing is, you might be aware of something really unsustainable like this bottle, which appears in the oceans and in rivers. What we're trying to do is we're trying to replace this material with a new type of polymer called PHFA, which is the exact same properties of that material, but sustainably sourced from lignin. So essentially, what happens with this material at the moment is cracked from oil. What we're doing is we're cracking lignin, a sustainable waste material from forestry, to produce the exact same material. And we're working with a very famous company that makes Coke. And so that's the type of work that we're doing. So all this work has been funded through lots of various agencies, but mainly through Europe. We're very active in European funding, particularly the circular bio-based economy, where we have been involved in and led 6 consortia, 5 currently running. We're going for 5 in a row this year. We had two in 1 year, so we're like the Limerick hurling team. We're trying to get 5 in a row. And we're also involved in national funded projects through DAFM, the Next Gen Wood project that was mentioned by Patrick earlier. We have a small part in that, but a very significant part. We've made some really big breakthroughs in that consortia. And we're also involved in two Spanish government funded projects where we're taking lignin out of forestry in Spain and making it to use high value products. And that lignin at the moment, you may have heard in the news, where there's lots of forest fires throughout Europe, and it's because of this lignin waste accumulating in forestries. That's why in the hot summers in Europe we're getting forest fires. So we're taking away that lignin, that sustainable resource, and bringing it into high value applications. So that's what we do in summary. But one of the things that I do, the thing I take most pleasure out of in all this work and all this research is that we've had lots of patents. We have lots of patents. We work with lots of companies, so we've had great impact. Companies license our technology, published a lot of papers, over 200 papers. H-index is 50, so which is really high. But the thing that I take the most pleasure out is the people that we're developing here in my research group. And I have the pleasure to introduce Aleksandra, who's one of those really talented people that are coming through from my group. So over to you, Aleksandra.
Maurice. So my name is Dr. Aleksandra Serafin, and I'm an RSc postdoctoral fellow in Maurice's Collins group. And I'm going to talk to you today about the implications of sustainability on materials used in health research. So as Maurice mentioned just a second ago, a lot of the focus of the Bernal Institute is to research materials and how we can take these waste materials and turn them into sustainable materials for good applications for our environment. So a lot of the ways that we can use lignin, as Maurice mentioned, is, for example, energy harvesting or energy storage. But another key aspect of the Bernal Institute focuses on researching strategies for health research. And this is part of the UN, so United Nations Sustainable Development Goal, particularly goal number 3, which focuses on health and well-being for all. So what we can do as material scientists is that we can use tissue engineering and apply this to achieve this UN sustainable goal. For those of you who are unfamiliar with biomaterials or biomedical engineering, what tissue engineering is that it merges the field of engineering, biology, and chemistry, amongst other fields, to basically provide regenerative strategies to tissues. So what we can do very briefly in tissue engineering is that we can have a patient who has some sort of ailment, and then we can, for example, take cells derived from this patient, incorporate them with biological factors, for example, growth factors, and put them into biomaterial scaffolds, which will make a tissue engineered graft. This tissue engineering graft can then be implanted back into the patient in favor of regeneration of this ailment at the site. So what my research focuses on specifically is to treat spinal cord injury. So spinal cord injury occurs when you have damage to your spinal cord via laceration or contusion, and basically this stops the neuronal tracts from working properly. So anything that you sense, that you feel, that you touch is transmitted by the spinal cord to your brain and back. So when you have this spinal cord injury, basically you are paralyzed from that point down. So if you're paralyzed in the neck, you're paralyzed from the neck down, basically. So what my research focused on is using these tissue-engineered materials to develop scaffolds to aid this regeneration, to prompt spinal cord injury healing mechanism and regeneration. So for this purpose, we tend to focus on materials such as alginate, hyaluronic acid, and gelatin, which are all biocompatible and sustainable materials. For example, alginate is derived from seaweed, so it is very easily gotten from the environment. Hyaluronic acid, probably a lot of you have heard on your TVs and commercials for different cosmetics. So hyaluronic acid is a natural part of your tissues, particularly of your skin, and it is now used in cosmetic industries as the newest regenerative purposes. Gelatin then, on the other hand, is derived from collagen, and again, collagen is naturally abundant in almost all tissues of your body. So all of these materials that we're using basically are focused to be biocompatible, biodegradable, and sustainable materials for tailored health strategies. So what one of my research projects focuses on the utilization of conductive nanoparticles, which we synthesized in our lab, in conjunction with these sustainable materials such as hyaluronic acid and gelatin to create these tissue engineering scaffolds. The reason that we chose to have conductive nanoparticles in our materials is the fact that the spinal cord transmits electricity signals up and down, and recent studies have shown that cells grown on conductive scaffolds actually have better regeneration than cells grown on non-conductive scaffolds. So we created these conductive scaffolds, and we characterized them fully, but I won't bore you with all the details, but in brief, we found that the mechanical properties of these materials were very close to the native mechanical properties of the spinal cord. So basically, we were replicating the natural environment of the spinal cord in a biomimicry manner. We then also found that with an increase in the p-dot nanoparticle concentration, we also saw a rise in the conductive properties as well. So again, we were able to achieve those good conductive properties. And again, as you are implanting these potential solutions into the body, we also had to biologically test them both in vitro and in vivo, so both with cells and with animals. So in the animal studies, we used male fisher rats, which basically had a spinal cord injury, which we then implanted our p-dot scaffolds into. And then after 4 weeks, we then looked at the regeneration of that tissue. So what we saw is that with the p-dot scaffolds, which are on the left, and the control, which is on the right, so the control had no scaffold implanted, it was just a spinal cord injury. So what we saw is that the p-dot scaffold had greater axonal regeneration at the site, so this is featured in green here in the top two, and also had lower inflammation in the tissue, featured in red in the top, and then red and green in the bottom. So basically, we had a much better regeneration with the presence of these conductive scaffolds than without. But we also do a lot of other amazing research in our group, focusing particularly on the utilization of lignin. So one of our PhD research students, Mohammed Mudassar, focuses on using lignin as a waste product for energy materials. So as Maurice mentioned, lignin is a waste product created in the pulp paper industry. You might think 140 million tons of lignin, that doesn't sound too bad, but just to put that into the perspective, if we were to cover the entire UL campus with 1 meter height layer of lignin, it would take 90 UL campuses to fit all of that lignin in. So that is a lot of material that we can then take and basically turn into sustainable and good materials for our planet. So what Mudassar does is that he takes this lignin, which is a waste product, and turns it into a lignin-derived spherical porous carbon materials for energy storage. But what he could also do is turn these lignin materials into lignin-derived membranes with hierarchical channels. And when Mudassar puts a salt solution into these hierarchical channels and creates a temperature difference between the top and the bottom, he's able to create electricity. So basically creating ionic thermoelectric materials for energy storage. So what Mudassar can do then is apply these two technologies, sandwich them together, and create sustainable materials, for example, for fitness trackers. So now imagine that you had a fitness tracker on your hand that you would never have to charge again, as it would be charging through the temperature difference of your body and the surrounding air around you. How amazing would that be, right? Another exciting research coming from our group focuses on the research made by Dr. Anne Buchan-McLaughlin, who also takes these lignin waste material and turns them into biosensors for sensing dopamine. Dopamine can be used as an early detection marker for Parkinson's. So what Anne does is that she takes this lignin and turns it into carbon nanofibers, and then with the incorporation of nickel through oxidation reduction reactions, she's able to create these dopamine biosensors. And what Anne has found is that these sensors have a very broad linear range of detection of the dopamine, and she also found that the workings of the dopamine sensors are very stable, independent of their storage conditions. So this is particularly useful, for example, to create health strategies and health detection to people in a variety of environments and storage conditions, making health research more accessible to all. And just to finish off with, as Maurice mentioned before, we have a lot of expensive bills that are paid by a lot of people, particularly funding coming from European Union, but we also have a lot of funding coming in from national funders such as the SFI, Irish Research Council, who fund my project, and also the Department of Agriculture, Food and Marine. And we also have a lot of industry liaison projects, for example, with Johnson & Johnson, BD, and PepsiCo. So thank you so much for your attention, and I welcome any questions.
Hi, everyone. My name is Matteo Lusi. I'm a lecturer here in UL, and I just want to present what we do in the molecular crystallography group. So I'm the leader of the group and the leader of the Irish Crystallographic Association. We work with crystalline materials. Anything molecular, crystalline, we're interested in. So usually we work with pharmaceutical and solid-state electronics, but recently we start working on separation and purification of molecule waste products and oil products, so derivative of oil. In the group there are 5 people, including me. And today I want to introduce Dr. Jacky Sorrel Bouanga that will tell you something that is relevant with the theme of this project, which is the environmental impact of our research.
Hello everyone, my name is Jacky, and today I will present to you the removal of nitrogen and phosphorus using zero light. Anyway, so there is no use for us to go to a nitrogen pollutant without knowing where it's coming from. So in general, nitrogen is produced by different industries and also by agriculture, which release nitrogen using fertilizer. But we also have animals and human waste, but also plants. So to that process, the nitrogen goes into the water and then goes into rivers and lakes. So the problem that happens is the accumulation of the nitrogen or also different type of nutrients. So this leads to this environmental problem where you have eutrophication. So what is eutrophication? Eutrophication happens when you have a high concentration of nutrients in the water, and when it happens, it helps the growth of algae. So those algae then will build up over the rivers, and then it will block the oxygen to go through, and then you'll have the death of different type of marine livings. So this is an example of what's happening at the moment, and it was given by Al Jazeera, and it shows that this is the agarase that is building up on the river, in the lake, And this also, all of this was will come out last year in 2023. And then the problem is still continuing with Lania Lake, where you can see that the agar is coming up again. And the only way for us to end this issue is to remove the nitrogen and phosphorus into our whole system. But this is not going to happen because we need nitrogen in a certain way. And if we do remove the nitrogen and phosphorus, we will have an economic problem, but also another social problem that might take place. Why? Because as you can see here, we have a lot of people depending on this system in general. As you can see, there is a track that happened, and it happened last year in Cork, where the farmers are coming out because of the nitrate legislation or limits that came up, which is not favorable to them. And we also have this happening here, which is a problem that is continuing. So another problem that can happen is that the nitrate limits does not suit the community. So because it doesn't suit the community, we have a lot of people that might lose jobs because of those different restrictions. So a way for us to really deal with this is really look at the sustainability aspect of it. So one of our ways is to look at the dairy industries. The dairy industry is a very large company in Ireland where you have the large production of various products. And then, but the problem is that we have different type of waste that come out of this dairy industry. So one of which, as you can see, the ammonium, the nitrate, and the phosphate, which has a very high concentration in their dairy waste, in the wastewater. As you can see, we have in Site 5, which is one of the industry where the water was analyzed, you can get 184 ammonium ppm content, which is quite larger compared to the recommended value of 10 ppm. And this is also happening for the phosphate, which is 8.1 and 31.7. That was found in those industries, which is quite larger to the recommended a value of 5 ppm. So a way for us to really work on this and maybe give a solution is to find a rapid, sustainable, and adaptable way to provide a solution that will work for every industry in Ireland. Our approach is to build up a technology which not only is going to contain, which not only going to help, which will help to treat the industrial water. So in general, the technology is made of filters where the wastewater from the industry will come out on this way and will be collected to that filter, and then the nutrient will be removed and leaving the water at disposable to the river, which will have very low nutrient content. For us, from the 2 years that we've been working on this, we've analyzed different type of nanoporous material. In this case, we've worked on zeolite. The zeolite will be used to absorb the nutrient content into the wastewater, and then this nutrient will then be regenerated later on. A published work that we have done is here. As you can see, we've used different type of material, and then we have an initial sample. This is the recommended level of ammonium. So as you can see, with our material, we were able to reduce the level of ammonium to less than the recommended value, which is really relevant for sustainability. And in this context, we've made a lot of testing, and we've completed more than 200 testing to find out which one is the best material to use, which will be cheaper for the industry, and which will be easily implemented into different industries. So at the moment, we're going from a lab work to an industrial work now. So we're building up a material, a technology which can be used as a multi-stage filtration, because we're trying to build up a material that is not going to only take nitrates, but it's also going to take phosphate and ammonium. So for that to happen, we have different type of material, and each material will look at a particular nutrient. So a way for us to do that is to build up a technology that will contain, that will focus on removing nitrates, and the other one will be focused on removing ammonium, and the other one will be focused on removing phosphates. And then at the moment, we're working on different parameters because we're going to implement it in different industry, dairy industry. So we want to adapt the technology to fit in every industry that we're going for. So the optimization of the residence time is more focused on how much water will be able to go through our technology. And then we're also looking at the capacity, because for each company, you will have a certain concentration of ammonium, nitrate, and phosphate. So for each company, we will adapt a certain quantity of material that will be used and implemented in the company. So the end goal is to have an output, a marketable filter process, which is going to look at nitrate, phosphate, and ammonium. And we also look forward to reduce the phosphate and nitrogen content into the wastewater streams, but it has to be sustainable, and it has to be cost efficient for the industry to be able to implement them easily. And that's it for me. Thank you very much.
So my name is Jacky Leahy. I'm going to talk about thermochemical processing of wastewater sludge for the circular bioeconomy. The first day we went into secondary school, we all learned that matter is conserved. Everything has to go somewhere. When you flush the toilet, it ends up ultimately a sludge. And when it ends up ultimately a sludge, it usually ends up in our research lab. So that's what we deal with. We look at ways of trying to valorize sludge. And the context for this, some of the speakers this morning spoke about it. It's the European Circular Economy Action Plan for Europe. So this went through the Commission in 2022. It has very, very lofty ambitions. And Patrick spoke this morning, so at national level, we had a national bioeconomy statement, which is more recently evolved into a national economy bioaction plan for 2025 to 2030. What we work with mostly is, in our research group, or at least what we're going to speak about this morning, is the new fertilizer regulation. So this was an enabling piece of documentation produced by the European Commission for recycling nutrients for agricultural purposes. So if we look at the European Circular Economy Plan, there are 5 components to it: production, consumption, waste management, and what we call secondary raw materials. And this was to be focused on a number of priority areas, which include some of the things we spoke about this morning, such as food waste, biomass and bio-based products, critical raw materials, and construction and demolition waste. These are considered to be the low-hanging fruits. So what do we mean by critical raw material? Well, the European Union has designated quite a number of these, but the most important one, probably in an Irish context, is phosphorus. So phosphorus and phosphates are what we call a secondary raw material. And ideally, the Commission would like to bring these back into a virtuous production cycle. To enable that, to create a market for secondary raw materials, the Commission, again, has a number of lofty ambitions. So they want to increase the use of secondary raw materials. So I suppose, to cause this to happen, they want to increase the use of recycled nutrients, and there's a document called the BAT document. So, and this is best available technology, and this is going to require all wastewater treatment plants to recover all nutrients. So all nutrients will have to be recovered. Aligned with that, the Commission also has, since 2022, has legalized what they call, or they've updated what we call the EU fertilizer regulation. And up until 2022, this fertilizer regulation only pertained to what we call mineral fertilizers. It has been significantly revised particularly to enable what we call bio-based materials to be included. So our area of research is to match these two together. So the wastewater treatment plants would be required to recover the nutrients. What we do is we look at ways of converting what the sludge from the wastewater treatment plants into products which will meet the requirements of the new fertilizer regulation. So in a perfect world, research world, as we operate here in our ivory tower, all things are possible. Unfortunately, the European Commission is a rules-based institution, so the only things that can eventually come back into this virtual consumer cycle are things which conform to regulation. So that's why we do what we do. So there are 5 annexes to this regulation. The first one, Annex 1, defines what your material is. So this is a fertilizer. So Category 1 tells us what type of fertilizer. There are 7 categories of material under this new fertilizer regulation. Annex 2, which is the other thing that we work on, defines what materials or what the regulatory requirements of the components going into these fertilizers are likely to be. So my colleague now, Marzena, is going to talk about some of the work that we do. Ireland is lucky compared to some of our European colleagues, because people talk about what is the regional opportunity. In Ireland, unlike most European countries, our food industry has standalone wastewater treatment plants. So currently, the Commission does not allow materials from municipal wastewater treatment plants to go into these fertilizer products. However, it does permit the use of sludges from standalone wastewater treatment plants, and that's where we are lucky. So Marzena is going to talk from now on.
So my name is Marzena Kwapinska. I'm working as a postdoctoral researcher here with Jacky for quite a while now, and at the moment I'm working for DPTC and on dairy sludges. But I will present the information here today, not only on dairy sludges, but also from previous from our previous projects and knowledge that we learned along the way when at the University of Limerick. So as it was already mentioned, wastewater treatment plants treat effluent and discharge clean water. But a byproduct of biological treatment processes applied has to also be removed from wastewater treatment plants on daily basis. And waste-activated sludge is separated from a treated water that is discharged to a local water body. And this sludge has very high surface area, and water held tightly to a surface of the sludge via hydrogen bonding. And even after dewatering, the water content in sludge is very high, 80 to 85% or even more. But the sludge contains also plant nutrients, which is phosphorus, nitrogen, micronutrients, as well as organic matter. And that's why it is used in agriculture as fertilizer. However, there are several issues associated with the current approach. Availability of tillage land, very high transport costs because mainly water is transported and nutrients are diluted, potential odors. And because sludge has high nitrogen content, to limit nitrogen losses, losses of nitrates to ground and surface waters, sludge cannot be spread on land when rain is forecast, where soil is waterlogged or flooded. Therefore, storage of sludge is required. And, but sludge is produced continually. Huge amount of sludge needs to be stored over winter, and during storage, the organic matter decomposes slowly, causing greenhouse gas emissions. And overall in Ireland, we produce around over 400,000 tons of sludge yearly from all the different wastewater treatment plants. In our research, we investigate whether thermochemical processes can offer a solution to address challenges related to sludge management. Hydrothermal carbonization is a process to convert wet feedstock at mild temperatures of around 200 degrees with water as the reaction media. And in this process, biomass is reacted in closed reactor vessel under autogenous pressure. And pressurized hot water is highly reactive. It acts as a solvent and catalyst or reactant. And many reactions are taking place, and all this transformation that occurs during HTC disrupts the organic matter structure, rendering it hydrophobic, and makes it easier to separate from the liquid, and also facilitates drying. So what we are getting after HTC is a slurry, which is easy to separate into solid product called hydrochar and a liquid. But HTC is not only a dewatering technology, or not only improves the watering of sludge, but also concentrates nutrients in hydrochar. And this is an example of nutrients that are concentrated in sludges, and hydrochars produced from dairy processing sludges meet all the requirements of the fertilizing product regulation, with the exception of hydrogen to carbon ratio, which is too high. And from 1 ton of sludge, we can produce from 60 to 200 kilograms of hydrochar with high phosphorus content. And this hydrochar is dry granular material, which is easier to store and transport. Fully assess potential of incorporating HTC processes in a wastewater treatment plant, we need to assess potential of using of the liquid product, maybe as a feedstock for anaerobic digestion. And this is what we are also working on in the DPTC Center in collaboration with University of Limerick, with Galway, University of Galway, sorry. Another process that we were working on is pyrolysis. And for pyrolysis, you need a dry feedstock. And pyrolysis is a thermal decomposition of organic material in the absence of oxygen and at higher temperatures, at temperatures around 400 to 700 degrees. And during this process, sludge is decomposed into a combustible gas and biochar. And the gas could be used on site to provide heat for the pyrolysis, while biochar could be used as a soil amendment. Pyrolysis has advantages because when it's carried out at sufficiently high temperature, above 450 degrees, it will decompose microplastics, and it will also remove substances containing fluor from biochar, like PFOS. We've been working on pyrolysis at laboratory scale as well as pilot scale, and we've tested various sludges, dairy processing sludge, municipal sludge, and also digestate. And from all the tested materials, only dairy processing sludge produces a biochar that meets all the requirements as per current European regulation. Also, hydrogen to carbon ratio is within the required level. So biochar does not only concentrate nutrients, but it also concentrates heavy metals if they are present in sludge. And this is why biochar produced from municipal sludge does not meet regulation, is not allowed at the European level, but does not meet the regulations, requirements of the regulations, because heavy metal content is too high. However, biochars, in some countries, biochars produced from municipal sludge are permitted to be used for production of biochar, and biochar is used as a soil improver, but not for food production. And we are also looking at transformation of phosphorus to find out how both processes will affect plant availability of phosphorus. And we do compare the different technologies. So although both processes are energy intensive, we think that they are suitable for sludge valorization in Irish context. Thank you very much.
So I'm moving on to myself now. So I'm here with my hat as, I suppose, a principal investigator in environmental research in the Institute, and my talk is on our talk is on ecological engineering and the bioeconomy. So the group that I work with, I'm lucky to work in the area of ecological engineering, and we apply these principles, I suppose, in two main facets. Sustainable treatment of contaminated waters using constructed wetlands, and the creation of engineered soils for application on the reclamation of industrial sites. To fit in with some of the bioeconomy, it's just that as we decarbonize the economy and move to clean energy, it is going to have a really intensive demand on critical or raw materials, on metals. There's lots of examples there, but just to, I suppose, maybe highlight the electric car, which I suppose is one of the things we're all encouraged to move towards for cleaner energy, is going to require 4 times more copper than a conventional car. And when we look at copper demand for things like offshore wind and batteries and so on, we're looking at the demand by 2050 is going to be up on 300% where we are today. And I'll put it a different way. We've been mining copper for 4,500 years. What we will need as a society in this century for copper surpasses what we've mined in the last 4,400 years. And it generates waste, or a byproduct anyway, because I suppose there is potential in many of these for valorization and reuse, but the byproducts generated can occupy significant land masses, significant footprints. And with that, we have the generation of leachates, the generation of wastes. They can be metal rich, they can be pH extremes, but ultimately they need treatment or contamination arises. And to give quick context, the eastern parts of the US alone have over 15,000 kilometers of contaminated rivers, 72,000 hectares of contaminated lakes. Our nearest neighbour, the UK, where they've this documented, they have over 1,500 kilometres of contaminated river. So it needs cleaning up. And conventionally, it's a labour and energy intensive process. The waters need to be pumped, collected, mixed. Chemicals need to be added. It's energy intensive, it's chemical intensive. And it's needed over multi-decadal timeframes. So it's huge capital investment and OPEX investment and short shelf life. So where ecology comes in is we're applying ecological principles. So wetlands are known as nature's kidneys. They clean up contaminants, they polish off water. And what we can do with engineering of this is we can optimize the process for treating waters, for holding waters that come off maybe in bulk volume and flood events and so on. So here's an example, I suppose, of what we're doing. And tying back into the bioeconomy, we're making a lot of these constructed wetlands, we're engineering them using, I don't like to use the term waste after our discussions this morning, but organically amended other waste streams to make soil materials. We make constructed wetlands and we can treat. And so the picture on the top is a site we've been working on, and you can see sustained over there about 7 years. We've been removing zinc out of the water to below threshold values, so that's safe for discharge. Another example, working with the pH extreme, we've been looking at a site again for over 7 years where the inflow pH is between 11 and 12. It needs to be less than 9 for discharge, and wetlands give continued treatment of that. So it's an ecological engineered approach that is both effective and sustained, and indeed helps us to achieve sustainable development goals. The other side of the research house, or the lab, is the creation of engineered soils. So I'm delighted to hand you over to my colleague, Dr. Mariagrazia Proto, who will take you through some of the steps, what's done there.
Good morning, everyone. Thanks, Ronan, for the introduction. So I'm going to talk briefly about my academic background. I'm Mariagrazia Proto. I graduated in chemistry at the University of Catania. Then I got my master in environmental science at the University of Turin. And then I moved in Ireland at the University of Limerick. And I got my PhD here at with the Bernal Institute and the biological department, and I'm currently working in the same research group, so with Ron Courtney as a postdoc. So today I'm gonna present briefly part of my project, of my work, that aims to produce, to develop, and also assess the engineered soil. But first of all, what is the engineered soil? So basically, it is like a soil which is created mixing different ratio of organic or inorganic waste that can, for example, can be like compost. So it looks very easy to create, but once we have it, once we create the engineered soil, we need to assess it in order to understand if it can be considered a soil with the same functional properties. So this is the approach that we undertook during this year. So first of all, we created different engineered soil using different organic waste. And of course, then we assessed it for his soil quality and soil function. Moreover, having the availability of 7 years of field data, we were able to assess the soil quality and functionality of this engineered soil over a long time, over a long period. The main findings that we obtained from this research are the following, and in particular, for example, I'm showing you here with this graph that the engineered soil show a higher accumulation of organic carbon in the first layer in his first layer, so in the first depth, 0-10 centimeter, if compared with the deeper one that is 10-20 centimeter. Moreover, the engineered soil that we created acted as a sustainable substrate for plant growth and development, and also showed a good and improved soil structure for both physical and chemical parameters. The two main areas where this engineered soil can find its application are the soil degradation, that is a very concerning environmental issue. In fact, we can see that worldwide there is a 200 million hectares of soil that can be considered degraded. And also in Europe, there is a 2.5 tons per hectare per year that can be considered like a soil loss. But also the other application is the contaminated lands from extractive waste, in particular, for example, the mine waste sites, that are as well a huge concerning environmental issue. In fact, for example, the mine waste sites have a footprint globally that is around 251,000 hectares. Then, to give you an idea, it's roughly like 193,000 hurling pitches. So in summary, at the very end of our research, that was published, we could conclude that the engineered soil that we created was a sustainable soil for plant development and growth, but also for the establishment of the ecosystem. But also very important is that the creation of this engineered soil allowed us to use organic waste, and this is a crucial point, a key point in the circular economy and the circular bioeconomy, because the waste can be reused and have a value and can be used as a new product for different purposes. Thank you for your attention.